Sam through the chat. My name is Paul Besley. I'm a principal technologist working with .NET since the beginning in QA, and this next 90 minutes titled .NET Async and You. And really what I meant by the title is that I think in sort of 10 or 15 years time, people are going to look back at the style of sequential coding that we do at the moment and think it was sort of rather quaint because time is moving on. Okay, so it'll be a mixture of some PowerPoint presentations and pre-prepared demos because it's in normal classroom speak we would do build it yourself demos, but it's a bit different over a webinar. So just some housekeeping stuff that if you've seen one of the previous sessions, you will have seen this before. So there is an email open, techweek@qa.com, for any comments about the Tech Week itself. If you like it, then please let us know. And then questions during the session, please use the chat tool. If things occur to you after the event, then there's my email address there, paul.besley@qa.com. Again, if I hope I'm speaking at an adequate speed. I noticed the line was a little bit garbled. I'll try and slow down a bit. Can you let Sam know if you have difficulty hearing me, and she'll communicate with me. Okay. Right there. Sorry about that. So here's the problem that the asynchronism is trying to solve. Two problems really. One is the top one that in the last, I don't know, 20 years we've been shrinking the dials of the CPU smaller and smaller until we're reaching the limits of physics now, and really it's the heat dissipation is the limiting factor, and that Moore's law is just turning out not to be true for the foreseeable future. The other thing is long-running applications or long-running processes. We need to keep the user interface alive. So there are two reasons why we need to do something to make sure that things are responsive. And in both cases, what we do is offload work, other threads, other CPUs, other machines. And the problem is that it's not easy. It's actually easy to offload work. The problem is coordinating that work and pulling it all back together. I've got a couple of pre-prepared examples of what you might see in the parallel world and why it won't go away. The first one I've got here is from the samples that come with Visual Studio. It's not a very convincing one, but it does a sequential and parallel. So there's the sequential, here's doing it in parallel. And I've got 4 CPUs on this machine, so you would expect it to go a bit faster. What was that, 3.2 seconds there, so now we're down. So it's marginally faster. So for my money, that's not a worthwhile improvement for the complexity that we're looking ourselves in for. A better one might be this sort of one here. By the way, I'll be using Visual Studio 2013, and all the demos that you see here will be available on the download site for next week. So what this does is it grayscales a set of sample pictures that come with Windows install. So if I run this and leave that as unchecked, here's the sequential sort of operation. So what it'll do, it goes through, I think it's about half a dozen pictures, and visual grayscaling is quite a compute-intensive sort of operation. And it should give a time again. There are 13 seconds to how many pictures that was. And if we run it again, and going parallel is as easy as checking that box. Yes, I wish it were. Then a little bit more overhead to get started. But once it gets out of bed, then the 4 CPUs kick in and give it down from 13 down to 5 seconds. So that's the sort of thing that we'd be looking at. Oops, forgot those. Where are we? There we are. So I could have done some cleanup in the code, I guess, on that one. And one that, again, this one comes with the samples with Visual Studio, and it's the statement that if you had enough monkeys, have 1 million monkeys and infinite time, eventually one of them would produce the works of Shakespeare. And so what we're looking at is thousands and thousands of combinations. And so it goes through and it tries to sort of, it favors those monkeys that tend to produce words that fit in with the intended script here. And here we are, we're what, 15 seconds through, and sort of about halfway through producing that particular paragraph. It generally takes about sort of 30 seconds or so. I'll do it again parallel, and we'll probably find it'll come out around about the sort of 15-second mark. There we are, 31 seconds, and it's got, I think it's pretty much got it there. Normally it comes up green, as it's got an ampersand in there. So if I run it there, if I run it again, this time do it in parallel, so that's 40 seconds. Then again, this is compute intensive, so all 4 CPUs should kick in, and it should do it significantly faster. Don't recommend it as a way of writing prose or anything. There we are. So pretty close, there we are, 19, 20 seconds. And just one other example closer to home, one that's actually on my to-do list, that QA has got something like 260 instructors teaching I don't know how many courses, and you can probably imagine the combinations of things that go on. That I happen to live in Edinburgh and end up teaching courses in London, where a London instructor gets shipped up to Edinburgh and so on. So here's an example of the sort of courses just in the technical area, say for 1 week, and we've in fact the presenter tomorrow, Matt Bishop and myself did this application together to do the number of combinations and reduce it to a manageable number to optimize the away from home for instructors. And it seems to work fine. It's actually on my to-do list of going parallel, because this needs to be client side, and having it just server side and buying bigger machines wouldn't be an answer. Okay, so that's the sort of problem that we're looking at, and what are the options that we've got. So let's get on with it. First of all, it's not just more difficult, it's much, much more difficult. So I would urge you, if you're going into the parallel world, and we all will go there really is a responsibility to make sure that your design is 110% correct before you start, because trying to debug it is like catching soap in the bath. You put the squeeze on, you think you've got it, and the problem moves somewhere else. So what technologies does .NET offer? Well, here's a bit of history about what we've got. We'll spend a little bit of time, not much, on the sort of .NET 1 ones, the thread and the thread and the queue user work item will feature. The async delegate, you'll probably find these things around in code that you see, but the way that we do it nowadays is very much down in the .NET 4 style here. 2005, they introduced the background work as part of the event pattern. So they've actually had 3 goes at solving the parallel problem. Sort of .NET 1, which really revolved around the asynchronous delegate, the event pattern, which is .NET 2, and now the asynchronous task pattern, which is .NET 4. And this certainly seems to have the necessary. I must emphasize, though, that even though Microsoft have done a lot of the grunt work for you, the responsibility is on you as developers, as programmers, to make sure that you don't try and use shared resources on different threads simultaneously. There's none of the things that they've got prevent that from happening. That's a responsibility that's down to you. And as far as I can see, always will be, but who knows. So the pre.NET 4 stuff. First of all, the thread class, and this is probably the class that you should never use. The reason being that how do you know, for instance, that 100 threads, which is what we've got here, is a suitable number of threads for your application running on this machine today, you didn't know at the time that you wrote this code what sort of machine it might be running on, whether it had accelerators, you don't know what other tasks are running on the machine. This is the only one that doesn't run out of the .NET thread pool. All of the other solutions run out of the .NET thread pool. And actually, the thread is also the one you can abort. It's highly recommended that you don't abort, but if you really do have a wayward application, all the others are cooperatively quitting the thread. You can, if needs must, you can actually blow it away. So I'm imagining that many of you have seen this before, so what I'll do is I'll briefly show some of these things from sort of prepared demos. So here's the example that's on the slide, winding up 100 threads, and what it does is it shows you the thread number as it turns out. And if I run it, then just freeze it briefly, you can see that it's actually, here's the thread number, it's actually using what's 99, probably 99 different, or trying to use 99 different threads. I've got 4 CPUs on this machine, so 95 of those threads will be just sitting there doing nothing at any one point in time. That's what the thread pool gives you, is management of the schedule management of those threads. And just to demonstrate that none of the collections in .NET up until .NET 4, none of them are thread safe. If I try and do this and add the thread number to a common dictionary, so here I've got a common resource, a dictionary, and if this was running in single-threaded mode, it would be no problem at all. I try and run it in multi-threaded, and bang, almost immediately it gives up. And the errors that it gives you can be very misleading, but this is the error I get here is because the dictionary class and all its sister classes are not thread safe. If Microsoft had made every collection of thread safe, then the whole of .NET would just run like a dog with no legs. That's different in .NET 4. There are blocking and non-blocking collections in .NET 4 that take almost no time, and they work very, very well when there are consumers and producers of those collections operating simultaneously. So here are the sorts of things that Microsoft looked at that they found us developers doing and tried to abstract those out and make them into an infrastructure, the task parallel library, that we can then leverage. So I've already mentioned how many threads is appropriate for the number of jobs I've got in the go. The partitioning problem, not sure I've spelt partitioning right there. So the partitioning problem is if I'm sort of holding a barbecue and I've got 10 guests and I've forgotten to buy any sort of beef burgers or buns for the barbecue, and there's a supermarket down the road, what's the best algorithm I could use? Do I chop my shopping list up into one item each, give it to each person at the barbecue and send them down? Well, that would work if everything were on separate aisles. If it's all on the same aisle, they get in each other's way, and it'd be cheaper and quicker to just divide the list into 2. So this partitioning is part of what happens for you in any of the threading models in .NET 4. Synchronization, that when they all come back together, you want to make sure that you haven't lost anything. I've already mentioned the thread safe collection, and I'll come on to the context that Windows Forms and Windows Presentation Foundation, WPF, both have thread affinity, meaning that you can only write to a control on the page, on the form, on the same thread on which it was created. And of course, built into all of these things is cancellation. And this is plumbed through the whole of the .NET 4 stuff. It's partially in the pre-.NET 4 stuff, but it's certainly throughout all the .NET 4 stuff. But we're here for performance, and cancelling unneeded work is all part of helping performance. So this closure, when I first came across this one, this slide, by the way, also shows the thread pool, which is the another one of the .NET 1 async options. So if I show you this on Visual Studio, when I first came across this, it seemed just that one. But here I've got a loop going 0 through 9, and I write out to the console the thread number, but I do this in another thread. Seems pretty harmless to me, and I would have expected this to go 0 through 9. I run it, and you get that. So you put in a debug probe to try and help and find out what's going on. So to simulate a debug probe, I'll sort of slow it down a bit. And now it starts to work. What's going on here? Well, this is to do with captured variables. So the way that .NET assembles this is it creates a dummy class and an object of that class, and then populates one of the properties of that class with that, which is because it realizes it needs that, a captured variable. And it takes a little bit of time to do that. And by the time it's ready to copy the value of I into here, well, I has moved on. I has moved on. In fact, it's finished the loop. So that's why it was 10 all the time. The solution is very simple. Is you do that. You capture value within the loop. And then hopefully we've got all the numbers there. It looks about right to me at a quick scan. And that's the closure problem. That's nothing to do with .NET 2, .NET 4, .NET 1. It's part of the way in which the captured variables were handled. So I thought I'd better share that one with you because you're not aware of it. It can cost you a lot of time. Using a lock. So the message here is yes, there is a lock. It's actually monitored or enter and monitored or exit. That lock is really like a macro that puts together that. And if we have a list, say here, of strings, and in this code here, what I do is I take 2 random strings, swap them back again. But if you do it just on one thread, like that, then Abel was I, you're Ice or Elder. Hopefully you sort of recognize that as being a palindrome supposedly attributed to Napoleon, who I don't think spoke English. If, however, you do it across a few threads, then it just gets itself into a twist. And not so bad that time, but it's completely random how it turns out, as you can see there. And the obvious solution to that is to put in a lock. So here's a lock across that, a critical resource that's accessed on different threads. So we'll say, well, this resource can only be actioned by one thread at a time. It's sort of a bit like the old railways, one engine and steam problem. The problem is, if you do that, I don't know if you noticed that the timing previously was about 200, you've effectively undone the benefit of multi-threading. So the message there is, if you use lock, think about a redesign such as to avoid any locking, because locking kills concurrency by definition. Exceptions, they're thread specific. Again, when I first came across them, I found it just baffling. So here we have the thread class, and in here, hopefully this makes sense to the audience online, in that this is a lambda expression, that what I could have done in here is have a standard method that is called a delegate, the thread start delegate then points to that method. And this is a shorthand for achieving the same thing. So imagine that's a separate method. If I run this and this throws an exception, I've put a try-catch block around it, and I would confidently expect for this out of range to appear here. So I run it, it throws the exception, it doesn't. Exceptions don't cross threads. So this exception here, if it's not caught in this thread, then it's just lost and can cause all sorts of subtle errors. That's not quite true of the thread pool. If I comment this out and instead introduce the QUWI, the thread pool QUser work item, this again throws an out of range exception, but this time it's caught. This is the behavior for all of the thread pool threads, which is, remember, is everything apart from the standard thread, that one there, is that if it throws an exception and it's not caught, then it'll be caught at the top level and close down the application. We'll come back to exceptions when we get onto tasks shortly. So they're thread specific. And just before we leave the .NET 1, because we're talking performance, thinking of asynchronous probably because of performance, there's another sort of gotcha that seems to be counterintuitive. So this is actually nothing to do with threads, but it's certainly a performance issue. Supposing I invent my own structure. The reason why I invent my own structure is because I want it to be sort of a quick and dirty type of animal, a bit like the ints and doubles, easily created, easily disposed of. And I happen to do an equivalence check like that. So what I've done is I've created a couple of rectangles here, done an equivalence check, and then put it within a timer somewhere there, so timer start, and cleared out the garbage collection so it doesn't interfere with the timing. And if I run it, we get a figure of, what's that, about sort of 60 milliseconds. And that's all there is in the struct there. If I override equals and do it again, remember 60 milliseconds down to 10 milliseconds, 9 milliseconds. I'd confidently believe that structs comparisons, when it did this sort of thing here, it would do almost a sort of bitwise comparison of the two elements in there and determine the go, no go, they're the same, they're not. Clearly it doesn't do that. Embedded in there is some reflection code as well. It actually gets even better if you override the operator equals, because now it doesn't even have to do a cast like it has to here. And it comes down from 9 seconds to 9 seconds. Let's do the operator equals. To just under a second. So the difference between 60 milliseconds and just under a millisecond is a huge difference, really, because the whole reason why you put a struct in the first place is for performance. Okay, that sort of brings us on to the end of the sort of .NET 1 story. Let's go on to, oh, I actually missed out the background worker, didn't I? So can I just backtrack? It's important that I show that. And the thread affinity of Windows Forms and WPF. I did this example on Windows Forms by the look of it. So what I've got here is a form with a couple of buttons on, right on the, and all it does, pretend it goes off and takes a long time to trawl its data, returns it and writes it back in here. So here's the wrong thread, and it does it on a different thread. Remember, this is a QUser work item that runs on a thread pool, and that's the problem, that it runs this code. Imagine it trawls this result back. It takes a bit of time to do that. The problem is it writes that on the wrong thread. With the second one, the background worker, which hopefully many of you will have come across, a brilliant little control. We have a do work, run worker completed, and what happens is the do work goes off and on a separate thread, and you put the result into its dot result. You then pick out the dot result from the one that went into here, run worker completed, and this runs on the correct thread, the thread on which the background worker was run, about that one there. So the context is passed through, and this one should work fine. So the first one should fail. What I do is I run it under debug, and it'll fail. Beware of this. That's a very simple control. It's not writing much text into it. If I run it with Control F5, it works. It'll work with a simple control and a small amount of data. Really the worst scenario for a developer, because you put it into production and it'll fail in weird and wonderful ways. Now, I'll run the background worker exactly the same way as I did the first one, and that works fine. So the moral of this little story is, when you're doing Windows Forms or WPF, you have to write to the control on the thread on which it was created. And sometimes you can appear to get away with it, like I did with running Control F5, but that's an illusion. It's going to catch you out. Okay, on to the .NET 4 story. And there are really different ways in which you can apply parallelism. I'll take you through in reverse order, because this is where you should end up. It's like, this is a sort of, not the destination of where you should be going, but this might be a convenient way, the data parallelism, of getting parallel behavior into existing code. But really, with the way that Microsoft are pushing us, I think quite correctly, is to move towards tasks and jobs. Think of this as being like workflow on steroids, if you like. And that I don't really care what threads it does or what loops it does, just do what you're able to as much in parallel as you can. So data parallelism means that we've got the same algorithm and we're running different data through it. So you'll recognize this from your for loops and your for each loops of current code. We've got non-blocking collections. There are a number of collections introduced in .NET 4, and we'll see one in a demo coming up, where because of the way they've constructed them, there's almost no locking. In fact, there is a tiny amount of locking, but that locking only occurs when the collection is being used very lightly, which is probably when you don't mind a bit of locking. Pipelining, which is where you can overlay. So if you've got a task A feeding task B, feeding task C, you don't need to wait for task A to complete before you can start task B. Likewise, B to C. So these are the blocking collections. It's surprising we've got non-blocking and blocking collections in .NET 4, but they serve completely different purposes. And we'll see this in the demo I'll show you. And then the task parallelism, where think in terms of jobs or tasks or workflow units. And the task continuation turns out to be a very convenient mechanism where you can chain tasks together, and this in itself morphs into the C#5 async await mechanism. So we'll start with tasks. So it's a promise of a result in the future. In fact, the original name of tasks was a future. It got renamed before the name of the class was future. It got renamed before the .NET 4 was released, but I certainly remember seeing presentations where it referred to it as future. So it's possible that we've got people on the webinar who are not that familiar with things like the lambda expression, which I showed earlier. So for the first task one, I'll work that from cold. and where are we? There. And build up the lambda from there. So we'll have a console app because there's no extra noise. Oh, no extra noise. There we go. So tasks. And what we'll have is a task which won't return value. And if we did that, we'd find it would error because what it's looking for here is one of these action delegates. And IntelliSense doesn't give you any clue that you can write something like this. I'd seen people write that and looked at IntelliSense and didn't help me at all. So the way I got around that particular problem was, well, looking for an action, let me create an action. And when I saw this, void brackets target, I immediately recognized this as being the signature for point me to a method, any method that takes no parameters and returns void. So I can do that. Static void. In fact, if one I prepared earlier, save me a bit of typing because my mouse looks a bit jerky at the moment. So this do work item here, what I'll do is I'll sleep just for half a second and then just print out the thread ID of what I'm on. And this can go in now. I start the task. Oh, I put the, to get the syntax right, put the action in there. Start the task. And keep the window alive for a bit. If I did that, hopefully this will then run. And it's running on thread 3, just repeatedly pushing that out. If I wanted to go to the lambda style, then what I would do is change that for no parameters goes into curly curly. And within the curly brackets here, that's where this goes. So we now don't need this. And we don't need that. And this is exactly the same as what I had just before and should perform the same thing. Actually, what I meant to do was to show that the main thread is potentially doing some useful work in here in parallel with the task operating. Okay. So that's what the task is. And what I showed you there was this one here where we have the do work inside there. We can have a task factory starting. These are totally synonymous. And if you want to return a result, so if you want to return, say, an integer from this, so this do work one returns an integer, then you give the generic version of task and qualify it by the type that's going to be returned. There are various ways you can connect tasks together. Here's a parent-child one. So I've got my parent task, there it is, and within that I start up a child task. And I say attach it to parent, which means that if I then kill the parent, I hose the children. So you can form a structure of your tasks like this that represents the business problem. Hopefully you're thinking, this looks a bit like workflow to me, and when I'm king of the world, what I'll do is replace the workflow with the task parallel library equivalent, because I think it contains all the necessary to do that. So if I run this, what should happen is we should have the parent task, do that and some more work, and then the child task kicked off in the middle of that. There we go. I think the child task must have a delay in there, but look at it. Yeah, 1 second delay, which is why it occurred there. And then we've got the continue with. As I say, this turns out to be really useful for a number of things, exceptions coming up, and also the C#5 async await combination. So if I do this, so after child 1, what I'm saying is when this finishes, then do child 2, sleep for a further second, and then write that out the console. So this one is now chained on the back of this one here, and both are children of that parent. Child 1, child 2, and we're done. So there we have the parent-child type of relationship shown with tasks, and also the task continuation. So we'll see the task continuation again. See it in this example where oh, sorry, that is the example I just showed you, the continue with. What I'm looking for is the continuation where we go into exceptions, which is the interesting sideline, if you like, task continuation. Let me show you that one. So what I'll do with this one, I'll show you it working from a sort of starter, and then we'll introduce some errors and different ways of treating those errors. So we'll start with a happy day, where here's my task. Notice a generic task is returning a string, happens to be hello sailor, and then this method here takes the task in, starts it, blocks. When you ask for the result, it will block if the task hasn't already finished, and then outputs the result. So happy day, hopefully this should work. There we go. And now we introduce a bit of bad luck into what's going to happen. We'll throw an exception in our task, like that. So this is one of the system pool threads. So it's going to give the behavior that we talked about just earlier. And notice it actually gives an aggregate exception. It'll close the task down because this hasn't been called. So an aggregate exception. The reason why it's an aggregate exception is because a task can chain other tasks, as we just saw with child and parent. So it could actually produce a whole slew of exceptions in one go. So it's not just one exception. That's why the task aggregates them together into the aggregate exception. So what I'll do is I'll change this for something that does a try catch around there. Like that. And see how we get on. So this time starting it, we're in a try block, picking up the aggregate exception, and then looping around all of the exceptions in there. In fact, there happens to be just the one. And in the example we've got here, then we should fall through into this bit here. Indeed we do. And it should still work in the happy day scenario. What's happened to my, oh, I've lost my happy day scenario there. So something like that. So there we are. So the happy day scenario works as well. Let me try something little bit more adventurous on this, because this is getting to be a little bit of a mess. Yes, we've got our error code separated out from our business logic, but wouldn't it be nice if we could sort of have a bigger separation between them? And what I'm thinking of is something along the lines of this. If I, for the time being, comment that out and drop in this one instead, where we separate things out a little bit more. So I said before I start the task, I'm going to continue it with this code here, so with this task. So after this task finishes, it's then going to run this one. Okay, this one, it's still got the business logic in it, but this is a step towards where I want to get to. Hopefully it still works, and we get the error code, and we get the happy day scenario. Are we running? Yeah, so it works with the happy day and with the error scenario. And now what I'll do, I'll make use of quite a nice feature of the task continuation. What I'll do is I'll comment that out. Which is this. That we'll have two separate procedures, one for happy day and one for error, predicated from this. So there are my two procedures. This code, the exception code, has gone into here. The happy day code, wherever that is, lost in this here, has gone into here. So two completely separate procedures. So I'll split it out really well. And then the task continuation is qualified, meaning continue with this task if condition A, continue with this task if condition B. And the conditions I've chosen are only round completion, do this. So if it was successful, do that. If it on any fault, go and do that. Now this splits out your business logic and error really okay. So if I now run this, there's the error handling. There's the happy day. So this task continuation can really start to split your code into business, raw business logic, unpolluted by error conditions and your error stuff. So that's the task continuation, shown here on the slide with those two variants. Okay, I showed you the background worker solution to this thread affinity problem of Windows Forms and WPF. Sure enough, there's a task solution to it, which is right here. First of all, we'll have the problem. So this time, it's like I've done it in WPF. By the way, I've used code behind clicks and that, which hopefully those of you on the air who are familiar with WPF would recognize that code behind is just not something that you should engage with in WPF, even though it looks like the right thing to do. That's very, very strong recommendation is to use the commands and go to a view model, so you have this would be completely empty. Anyway, let me start with this, and what's happened is that I've on the go click, so this button here, which operates, I think it's just this progress bar. The others will kick in a little bit later. Operates that progress bar, and it'll try and, there we are, do some work. Progress bar 1. This do some work will be on the wrong thread, so when it tries to do this, it should throw a wobbly. So try and do some work, write a progress bar, bang, game over. Different thread owns it. So we'll see if we can fix that problem using the task synchronization. Sorry, the synchronization context to give it this proper name. First of all, we'll add in a variable at the class level to store the context of the main thread, which is that. We'll then, when the go button is clicked, what we'll do is take our current context and pop it in there. If then we did this, hopefully some of you may realize that this is wrong, because what I'm actually doing here is I'm saying this task that I want to run up here, make it run on the same thread as existed here, meaning make it run on the main thread. So I've achieved absolutely nothing by that, and it should give exactly the same error. Just realised I started it with Control F5 by mistake, and can you see it's sort of in fun mode? I can't do much with it. We're only starting with debug. Oh, still in fun mode, which is in .NET 1. That's sort of what used to. Oh, sorry, not fun mode. What's happening here is that it's running on the main thread, so it's waiting for the main thread to finish. It's all locked up. This is the reason why we went async in the first place. So we don't want that there. What we need to do is to offload that. WPF might use its dispatcher to do that. What we'll do is use a task to do it and run that task in the context of the main thread. So instead of that, we'll do that. There's the UE context. So that says this might be running on a different thread, that's fine. But when you get here, make sure this thread that you start is on the same thread as existed there, which is the main thread. So hopefully this should solve the problem. And this should be responsive. It is. The taskbar increments. There we go. And we'll come in and fill the other bits, the cancel and the check status, in just a minute. So I'll leave this Visual Studio around just for a little bit. Skip back into sync. There we go. Okay, so the synchronization context is what you need instead of the background worker when you're thinking in terms of tasks and thread affinity. And thread affinity really means Windows Forms and WPF. Cancellation plumbed in throughout the whole of the .NET 4 parallel story. And we'll see it again when we see the parallel class, which I mentioned earlier, which is a sort of halfway point. So the parallel class allows you to do things like parallel.for, parallel.for each, allows you a sort of in to get your stuff parallel, get your existing stuff code parallel. So let's see the cancellation of this and see if we can get it to work with the demo that we had just now. I can get the demo back in, I'm sure I can. But just before I get the demo back, the way that they've constructed the cancellation is they have a producer responsibility and a consumer responsibility. So it's split into two parts. It's not like there's a cancellation token, everybody can set it and everybody can read it. There's a cancellation source where the owner creates one of those. And then from this source, a sort of factory pattern, it'll pass down tokens, or sorry, you get tokens and pass them down to your code. And you can poll, you can request a callback, you can sit on a wait handle against one of these cancellation tokens and take the appropriate action. So it's definitely a cooperative system. And you as a consumer, if you're the task that is going to be cancelled, the reason why they've done it this way is so you can't inadvertently cancel some other task. In other words, cancels can only occur from the person who's got the cancel token source. This one here, the token one, won't have a dot cancel on the interface. So let's see if we can get that going here. So what we've got, excuse me, let me introduce the means to be able to cancel. Like I did here, the means to be able to switch to the UE context. What we need is a cancellation token source. And what we need in our cancel button is to call .cancel or not. And I've lost a curly. There we are. So I've now got the ability to cancel things from which a token should be created from here and passed down to cooperating tasks. So what I'll do is I'll actually replace this single progress bar update with a multiple one. And I'll obtain a cancellation token from this cancellation token source. Okay, so I've now got 4 tasks here, all hooking into a variant of that. A variant of that which will take a cancellation token as its second parameter. So let me do that. So the bit of new code introduced here is I'm passing in a cancellation token, and then cooperatively, as you notice, I'm polling it to say, do I need to cancel? Do I need to cancel? Do I need to cancel? And this is the means by which, once it's decided, yes, I will cancel, I will let others know. And so what should now happen is I should have now 4 progress bars kicking off at 2-second intervals. And then if I cancel, I press that, then this should then have the .cancel, should be picked up by all the tokens that were spawned from it, which go in here. They come out here, and it should be picked up here by each of the tasks that is in progress. Let's have a look. Well, I did a Control F5. It's best to do just out of habit. I do Control F5. So let's do a debug. So there is a cross-thread exception. I'll definitely pick it up. So if I start them, the other tasks should start, and then if I cancel, we stop, and they come back as cancelled. Like that. Okay, so far. So again, I'll leave this demo open because there's one more thing to do, which is the wait, which we'll do in here. So the cancellation mechanism, token source, and cancellation tokens. Finally, in this section, the wait. Wait all, wait any. Hopefully, sort of fairly self-evident that here you can wait on all of a set of tasks completing. Here you can wait on the first task that completes, then off you go. So let me add a wait into what I've just done. So first of all, I'll make a note of the tasks that are in progress, such that I can cancel them. I'll get their status. So what I use is one of the non-blocking .NET 4 collections, concurrent bag. There is no concurrent list, strangely, in .NET 4. Well, I thought strangely, but when you think about it, actually it does make sense because you're running on different threads, you've got no guarantee as to where you get in the sequence of a list, hence the concurrent bag and not the concurrent list. And we'll add in our 4 tasks. There we go. So at this point here, I should have a concurrent bag collection here containing my 4 tasks. And in the check status, what I'll do is what? So I'll sit on await all, meaning when all of these tasks are finished, then issue that. And no matter how finished or abandoned, cancelled, it responds to both. So what I'll do is I'll wait until certainly one task has finished and the others are in progress, then I'll cancel, and that should trigger this to say, well, they're all done now, it should complete that. And then I'll go around all of the tasks and you should see that some are completed, some ran to completion is the phrase, some are cancelled. Again, I did Control F5. So if I let them go, so I'll wait until this one completes. I'll cancel once one of the others is in progress. There we go. So now 3 have cancelled, 1 completed. If I do this, it should now, on the task wait all, it should say, well, we're all complete now, let's go. And it'll tell you the status of the task. So 3 of them cancelled, and then 1 ran to completion. So that's the wait all. Okay, I think we're done with that demo. Must have forgotten to put a solution file in. Okay, so we've been through the task story, which consists of being able to create a task, typically use the task factory to do that, the parent-child, the task continuation, the conditional continuation of tasks, which is really very handy, and then the synchronization context, which is where you can say to a task, I want you to run on this thread because it's important that you do. On to another mechanism for parallelizing, which is pipelining, or sort of conveyor belt, where you can start working on the wheels of your car on the conveyor belt before the car's engine is completely installed, or whatever the sequence is in the Ford factory. So here's the sequential story, and wouldn't it be nice if you had the ability to do this? And yes, in .NET 4 we have the ability to do this. Firstly, I'll show you a clunky way of doing this, sort of pre.NET 4, and then show you why they produced this blocking collection to solve this problem. So we'll start off with a clunky implement function that what we'll have is a number of threads here. There we are. So we've got 0 through 3 threads, so 4 threads, and we've used random numbers and put them into this list. Remember I said that these are not thread safe, so I'm putting them in without the lock, and then taking them out again without the lock. And yes, we should expect fun mode not very far into this process. Let's see, if we ran just on one thread, we would probably never notice that we were heading for difficulties. So it took 45 milliseconds. If we run across 4 threads, then almost immediately we get bad things happen. And it's not particularly obvious as to what the cause is. Index was outside the bounds of the array. Well, that's what the runtime thought the cause was. The true cause was that I'm manipulating a shared resource on different threads, and I shouldn't be doing that. So a clunky solution to the problem would be to do that. Notice this is really clunky anyway, that on the consumer side, see what I'm doing on the producer side, I'm pushing work into this queue. Okay, it's not much work, it's just numbers. But think of those as being jobs that I'm pushing into the queue. On the consumer side, I'm taking them out of the queue. And what I'm doing is I'm just sitting there forever, waiting for the next item in the queue and taking it out. So a very lumpy type of implementation here. I'm not proud of this, but it should at least work. The problem now, of course, is that I've pretty much removed all the benefit of going parallel. And so it took, what, 4 seconds to go through that lot there. And that's because this was locking it like mad on the consumer side. Let me change this to be the .NET 4 pipeline solution. First of all, in a parallel world, this is death. You don't want thread unsaved collections. So we'll be dumping this. And we'll be dumping this. In fact, we'll be dumping all of this because doing a while loop like that is really not very smart indeed. What we want to do is to be able to put stuff into a collection here. So I'll have a blocking collection. There's my blocking collection, thread safe. And one of the things I can do with this is add to it. So I'll add my random number into my blocking collection. And the beauty is I can take it out of the consumer side without any fear of interaction between the two. And the way that you take it out in the consumer side is not just a for each in the blocking collection. You actually use the method, not particularly obvious by its name, get consuming enumerable. Probably could have done with a better method. What this means is, if you look in this collection and there's nothing there, then sit there and wait until there is. And don't consume resources like we do here, looping around. As soon as something goes in, then take it out. So I'll put the numbers in, take the numbers out, because there's so many numbers, I won't sort of pump them out to the console. Hopefully you'll take it on trust that really they are going in. And the same as before, we'll add those to the producer's collection. And we let it run. I think it was it 6 seconds before? And now we're down to something like about 2 seconds. And this is doing just as much work as it needs, far less than this was doing, but this had no means of doing it any smarter. That's what the blocking collection is. It's a push in, push out, pretty much without locking. One further adornment you can do is after we've finished all the producers, which would be here. So wait for all the producers to finish, and then you can say, I'm done with this queue, which means this would then exit, and you're not consuming resources there either. So the demo I've got doesn't actually show that, but you can take it on trust. I'm an honest sort of guy. Then the consumer has now finished. So that's the pipelining pattern. My experience of the pipelining pattern is I was really very surprised at how beneficial that was. I was expecting the other sort of heavyweight patterns like the task to really sort of make a big difference. But I found the biggest difference was overlaying the tasks using sort of pipelining. Okay. Right, and into the parallel. So as I mentioned earlier, where you should be aiming for is the task sort of world. As a stepping stone to get there, think the parallel class. And what the parallel class offers is where you might have this in your existing code, a for loop for each loop, then it's a parallel.for, and the contents that you have here ends up inside this lambda expression here. So here's the current index. Remember, these won't necessarily go in sequence. Parallel means parallel, do in any order. And it's got an algorithm in there to avoid something called false sharing. If you come across that, it's a bit of a subtle thing to do with the caching of level 2 cache on CPUs, but that can cause things to slow down dramatically. And again, they've accommodated that in these models. So parallel for and for each. Do I need to show those? I'll show the next one, the invoke. Actually, what I could do is show the parallel fork done from cold. Yeah, let me do that. So if you have an existing loop of something like that, some sort of task inside there, what I'll do is I'll just print out the thread number just to give it something to do, and I run that. By the way, whenever I'm putting in a console read line, that's really being a bit lazy. What I should be doing in the parallel world is it's a wait. So this is to stop the main thread finishing, and hence having no further use of spawn threads like this. So here we are running sequentially. Not running sequentially, of course, yeah. And so they're all on thread. Happens to be thread 1, yeah, different thread. So no, it's a random process. If I now make this parallel, then that is replaced by the parallel dot for minimum and max and minimum. I think they describe this actually quite well. From inclusive to exclusive. It's a bit better than the terse C syntax. So ends up as the same numbers. And then here, this is the lambda. So I goes into, and if you have a multi-line, it would be that. We haven't got a multi-line, so we would have something like that. I think that's right. Seems to compile. And now the threads can go in any order, as indeed they do. And notice it's 1, 3, 4, 5, 6. I've got 4 CPUs on here, so it's tried to use 4 threads, had to go with 5 and probably realized that's not a great solution and probably gone back to 4. All that work is done on your behalf. So there's pretty much what's on the slide here, but the formula for each is about the same. You can have the invoke like this, which lines up a number of delegates like this and then fires them all off, and it won't go past this point here until they're all complete. The quitting of the parallel for is quite interesting. Sounds like Stephen Fry, doesn't it? Not quite interesting, but it is quite interesting in that what they've built in is a couple of things of interest. Firstly, you can specify the degree of parallelism. Now, this is really great because what you can do is you can test it like that, you unit test, and then do another unit test with it running in parallel and make sure that you get the same results. The second thing, or the reason why I popped into this for this particular example, is because of the state. Now, one of the overloads of here, you pass in the index, the current index number, and the state. And what you can do here is break or stop. Stop just stops it in its tracks. And what break does, which is quite interesting, is it will attempt to run iterations up to the failed one, even if they haven't yet started. So what I've done here is when index 5 is seen, break, and probably a couple of threads prior to index, a couple of iterations prior to index 5 won't even have started. So if this works, then what we should have is index 5, and then after index 5, a couple of others lower than 5 actually complete. Or start and then complete. So 5 is finished, Oh, it actually didn't do 5 until a little bit later on. Let's try it again, so we get different results. Let me try changing it to 6. Seems to be today popular on 6. 4, 6. There we are. So we cancelled on 6, and sometime later, even though 1, 3, and 5 hadn't even been thought of by the time the cancellation for 6 occurred, they were still run. And so at the end of the loop, it'll say, here's the iteration, and it was good up to that point. So in other words, it'll give you a feedback to say, which iteration it was good up to. So that's the quitting of the parallel for loop. P-link. Your best route into a parallel world tomorrow is probably to do link today, because for the sake of 13 characters, you can convert from P-link, from link to P-link. Let me show you an example. So here's the canonical method for calculating a prime, always used in these sort of examples. It's not actually in my contract to show the is prime like it is to show hello world, but it's pretty close. And so what I've got here is a standard link statement that runs on same thread and just iterates around from 2 to whatever that is, 40 million maybe, 40,000, and figures out whether that number is a prime number. If it is, puts it into the output like that. At the end, what we'll do is add up how many of those we've got. Somewhere here, list.count. See how we get on. So if we run it, and it took 3 seconds, and we got 283,146 primes in that range. But this is running on one CPU, one thread on one CPU. I've got 4 CPUs here, 3 CPUs just sitting there, I don't know, watching Neighbours on television. I'm not doing very much at all. Wouldn't it be nice if I could just make a small change to this to say, make use of those other CPUs? And that's these 13 characters, dot as parallel, bracket, bracket. What that'll do, it won't do it for link to other things. It's just link to objects and link to XML. It'll make use of the other CPUs up to a maximum of 64 CPUs. So now when I do it, I forget how long it took. Was it 3 seconds previously? Now it's about half the time. Same result. Brilliant. So that's why I say, certainly on all the courses I teach, try and do link today, because tomorrow, for almost no effort, apart from testing effort, of course, you can get the advantage of the CPUs that your hardware guides have installed with. Okay, so now we're 6:15. On to the C#5 story. And what I'll do is I'll build this up because it comes from the task story. I'll tell you what I'll do. I'll show you a second P-link demo, because that'll set the scene for the mechanism we're going to use here. So what we've got here is another P-link demo. We've got a number of addresses here. You probably recognize some of them. And so we're going sequentially, and we're firing off to each of these websites and saying, do me a web client request synchronously, pulling back the page and then counting how many bytes are on the page and putting that out to the console. And we're doing all this synchronously, and what we'll do is we'll parallelize the whole lot. So we're going sequentially now. So 43,000 bytes on the QA page. You heard it here first. If we now do it as parallel, by the way, that number will change because it's got things like date in there and time. If I now run it again, hopefully you can see quite a bit faster, making use of all of the CPUs there. And I'll use this example in the building up of the C# async await story. And I'd ask you to note that in here, I can use the asynchronism is not in here, but it's in here. In other words, it's outside of this loop. The reason why I was able to take advantage of this is because I've run the same function, I don't know, what is it, 10 times. What if these were all different functions? Well, this would sort of break down somewhat in that respect. And that's what the C# async story addresses, is what if, I'll ask you to pretend in the demo coming up, that actually what I've got here is 10 different functions, not 10 functions that are the same. And we want them all to be asynchronous. So let me switch out of that. And into my starter. Oops. Instead, let me switch out of it. What I meant was, let me stay in it. Here it is again. Slightly differently, I've just limited it to 10 instead of having it on the previous one. So notice what I've done. So I've left in when I was testing it. So let me put it back to as you saw it just now, and we'll build up the story. So and change that to synchronous. So this is pretty much where we were just now. By the way, if you ever do come on QA courses and do the labs, and you find that we've copied the solution into the starter, this is exactly the problem I just experienced on myself here, is that when you've got a lot of these things on the go, it's just fiendishly easy to fall into that trap. Anyway, here we are back to very similar to what we had just now. Imagine these are separate functions like I've got here. So I can't lump them together into something like a link statement. They're all separate. And so they have to run sequentially. So the sort of behavior I get is what we experienced first off, like that. Okay. How can I do better? Well, what we'll do is we'll change that and do it as a traditional asynchronous, something like this. So if I just introduce that back again, purely so I can do a change of this, snap that, and then change that to a sync, but two methods. So you notice there are two methods here. Stick that back as it was. Okay, so there we go. My casing is correct. Yes, I've done it. Async is two methods. You kick it off, like I've used the background worker here, and then you have a callback to say, well, when it's done, here's the code. So it's split into two chunks like that. It works, but it's a little bit clunky. It's sort of in your face. Is there a way, possibly using tasks, that we could improve on that? And big surprise, yes, there is. So what I'll do now is change this to try using tasks. put that back as async two methods. By the way, all of these demos will be available, so the reason why I'm preserving them like this is such that if you wish to, you can retrace the steps that you're seeing here. So I'll try using tasks, in particular, task continuation, to do what we saw as the callback here. So here we're using tasks, so creating up a task here, which is running asynchronously, which is great. And then when that's finished, we're saying, and now run this task to do something with the result. And you're probably looking at this and thinking, well, yeah, it's using tasks, but it looks a bit messy to me. And I think you'd have a lot of people agree with you, but it does look rather messy. Wouldn't it be nice if we had a way of doing this? Let me preserve that for you. If we had a way of doing this with a bit of sort of keyword help that eliminated the syntax noise here, but kept the principles of what was going on. For instance, what we want to do is, if we return a task here, we could probably go straight into something like that. So if we return a task, string task async, so this will be a task on the left now. I'll leave it as page just for the moment. We don't mind that because that looks exactly like our regular sequential code. I prefer not to have that line there. So wouldn't it be nice if we had a bit of a keyword effort to get rid of that and get rid of some of this noise as well. This continue with, it'd be good if we had a keyword such as await that meant exactly that. That means we wouldn't need to do that either. In order, remember we've deleted some of the syntax going on here, so we need to do a bit of this. And then the final bit of magic, pixie dust that was applied, was you notice this compiles now. Even though this is returning a task, this transforms it such that, because it's always the result that you want from here anyway. So page. And that's how the async await combination works. It didn't require any change to the .NET runtime. It's purely a compiler thing, which means there's no new features involved in this. It's using this, the task and the continuation mechanism, in a very logical way, because this now looks like the original procedure. In fact, there's the original procedure. It's almost a case of spot the difference. And the difference is that the thread will come in here, it'll reach that point there, and then it'll return. And at some point later, when this is finished downloading, it'll then come back and do that bit and that bit. But the in-your-face code complication is exactly what you see here. It just looks the part. Let's hope it works. Yeah, and notice I didn't draw attention to the startup cost, but the startup cost of doing the async await is a little bit more than some of the other mechanisms in here. For my money, that's a price worth paying. So that's what we started with. We then split it into the traditional asynchronism where you get a callback like this, split into two methods, and that's what we've been doing for 10 years. And it gets messy, particularly when everything is asynchronous. If we'd started to use tasks in it, then this ain't so hot either. I think your eyes just sort of rebel at the number of sort of curly brackets and syntax fluff that's around them. That's where the keywords come in, to remove all that syntax noise. And I've got one of these complicated PowerPoint builds on this. Let's see if it works. So that's what we started with. We want to get rid of that, and the async keyword replaces that, if you like. We want to get rid of those and have the task async in return a task, and the await keyword helps us with that. And the final stage is this actually returns the result and not a task which contains a result, and hence this needs to change as well. It took me ages to do that PowerPoint build. I'm glad it worked. And as a comparison, there we go. So the synchronous and the asynchronous, very, very similar. Under the hood, completely different, but the mindset that you need is not a huge shift. I guess the problem is that they're contagious, that the caller of this has to be asynchronous, the caller of that has to be asynchronous. So you end up with chains of asynchronous. And actually, it's only the deepest one, the deepest await, that actually sits there waiting. Once that's done, they all just ripple back. So this is the sort of world that I think is ahead of us. Okay, just bumping up to 6:30. Just as a brief summary of where we've been to. As I say, I think in 15, 20 years' time, synchronous code will be looked at as this is the sort of stuff they did in the 90s and the first decade of this millennium. Isn't it nice? But did they really have to do it that way? Because it's just not performant. The parallel class is something you can use today with care. Remember, in all of these things, you have to take responsibility for accessing common resources and making sure that they're not messed up. But there are non-blocking collection classes to help you with that. And where we finally want to end up is with tasks and the C#5 async await is a way of implementing that, which makes your code look, I think, very neat and understandable. So, if you liked what you saw here, the sort of things that QA can offer you, I've listed here. I don't need to read them out, but there's a number of courses, and probably all of the material that you've heard this week, it's in some way relates back to courses. If it doesn't, then we offer tailored courseware as well. Oh no, and a little afterthought. I shouldn't have put it as an afterthought, but bb.net courses as well. bb is not forgotten. And lastly, the housekeeping slide again, just to remind you that there is an email address, techweek@qa.com. If you liked it, then my name is Paul Besley and the session was .NET Async and You. If you didn't like it, then my name is George Bush. I hope you did like it. I hope it's a good investment of your time, and look forward to seeing you on another session. Okay, thank you very much indeed. So, I'm going to stop sharing. There's something I need to do, Sam? Are there any questions coming through? I can't see anything.